Hey, welcome back. This is Shop Talk number 26 for May 2022, and this is where I show you my barbecue and my construction projects around the house. Just joking, this is a machining channel. I have a little bit about grinding a drill press spindle. I showed grinding drill press spindles before, but this time I showed in detail checking the taper angle by bluing it up with a master, in this case with a drill chuck used as a master. Also, I have a section about my commonly used grinding wheels and what to boil them down to. So as you can see, we're grinding another drill press spindle here on the surface grinder, and the new BMA grinder with its way larger work envelope than my old lip surface grinder has made a huge improvement in doing the setup very fast and easy. For one, the additional C height, or in case of a surface grinder, that's the Y-axis moving up and down, if you go by the correct nomenclature. Correct nomenclature on a surface grinder: table traverse, X-axis. Grinding wheel side to side is the C-axis because it's in line with the spindle. On a machine tool, always, if you use the right nomenclature, the C-axis is in line with the spindle. On a lathe, the bed slide or carriage is the C-axis, and the compound slide is C0 because it's at 0-degree position, also in line with the axis. And the height movement on a grinder is Y. This is basically the same as a horizontal mill. There is a ISO standard for that, so not terribly interesting, but maybe good to know. The additional height here allows me to use a proper sign plate. I bought this years ago from my day job. They wanted to throw it out, and I got it along with the Moore rotary table and some other stuff. And on my lip surface grinder, this is way too tall to use. And I have a magnetic V-block on top of it, and the drill press quill with the spindle mounted in it sits on top of the V-block, and I just have two woodworker clamps, F-clamps, Bessie clamps, whatever you call them, giving additional safety because the V-block holding on this quill is not crazy strong. And I don't want to fling the whole quill across the shop. I have a hacked apart electric screwdriver here running off a lab power supply down here. That's what I use to run a motor in this thing. And O-ring and a pulley that's bolted to the spline drive shaft of the quill. That's the way I grind this. And what's also making this very nice for grinding, since I'm sitting in front of the machine like this, I have I'm constantly watching the progress of grinding, and I can easily traverse the table out like this, Have my drill chuck that I use as a gauge, blew it up, check my fit, which since I'm using a sine plate now, I usually hit the taper angle on my first try and don't have to adjust anything anymore. So that's a huge improvement, making things very, very nice. And when I want to go back to grinding, I just traverse the table back and lock the table in place using the stops. So there's grinding position. Also the DRO gives me a good reference how far to go down or traverse over, because you don't want to run into the shoulder here if you don't have to. So yeah, that's a grinding setup for drill press spindles. You could also do a grinding spindle with an outside taper with this arrangement. To grind an internal taper, you would have to rig up a high-speed spindle that can grind IDs. The spindle on this grinder, the spindle itself is a Fisher spindle, I think, that can run up to 40,000 RPM, but it's limited by the motor, of course, because this is just a 3,000 RPM motor, and due to the belt configuration in here, it runs 5,000 and a little bit on the grinding wheel. You could overturn this with a VFD to get about 12,000 on the grinding wheel, and then I could put an arbor on it and run a small ID grinding stone, but I'm not sure yet how I'm going to proceed this. I would much more like a small high-speed spindle that goes, that's mounted 90 degrees to the spindle, so it's pointing in the direction of the table traverse. That would be much more useful for ID grinding. Steve over at Solid Rock Machine Shop, sorry Steve Barton. He has such a setup with a NSK Planet 500 air spindle on a surface grinder, and it looks really like a useful setup, and I absolutely want this on this machine. That's also the reason why I got a machine with ball or with roller element guides and all access, because you can do stuff like that without having to worry about tipping the table or something like that in case of hanging stuff off the side of the table. So let's proceed on grinding this taper. While we're here, I will look at the grinding wheels that I use commonly later, but first we have to finish this. So this was a 0.01 millimeter depth of cut, means 0.02 millimeters in diameter. And now the magic, whoop, get the table out. As you can see, the taper does not clean up, and it won't, because there is really heavy galling back here, but the galling is below the surface, and we still got a huge bearing surface here on this taper. And I really do not want to draw this taper back much more, otherwise we will have to shorten the thread here, and the customer has to shorten the nut that's used to push the chuck off the spindle, and it creates a whole lot of additional, well, not problems, but issues. So just to give you an idea how well this taper runs after grinding it in its own bearings, this is a 2 micron indicator. We have contact. Let's zero it out. This is truly not bad. That's how most drill press spindles come out after grinding them. The trouble with checking tapers is you always need a taper master. You can either buy one, very expensive. You can make one if you're set up for it, like ID grinding, but then you still have to check it. You can check them, for example, with with 2 gauge balls that different size that you drop in the taper, and you check the depth that the ball drops to with a very precise indicator, and do your math and figure out if your taper of your gauge that you made is correct. Or you use a known good taper like this room drill chuck, which I trust. And then you need some high spot glue. In this case, I'm using the die-cam stuff because this gives a very, very good print. That's also the reason why I wear gloves, because stuff never gets off your fingers again. And to apply it in the taper, I use an old Morse taper wiper. This has proven to work very well. Just a little bit well, that's a little bit more than a bit, like I'm on the leather of the wiper. Try to get even your gloves clean. And then you can just use this to put a thin layer on. This is you will get some practice on how heavy the blue has to look to get a reasonable result when doing your checkup. With the die-cam, it will always look relatively dark because die-cam has a very heavy pigment in it, but it spreads out very thin. That's why I like it for tapers. It shows very precise print. And you get just an even coverage all around. That's the benefit of using the wiper here instead of trying with your finger or with a piece of shop towel or something like that. So the next thing that I constantly see people do, they take their master or gauge onto the taper and they spin them like crazy. Spin them back and forth, and just with your hand motion, you will make every taper fit perfectly that way. You will cantilever it slightly, will spin it, and that way you will nicely glue up the whole taper, but that's not what you're after. You want a realistic representation of this taper in relationship to this taper. Otherwise, we could just skip this and have dinner. So what works, or what works better, is you take your master, you put it on, you press it on. We don't spin it around, we just press it on, and then we get it off again with a very minute spinning. And even this, as you can see, this is a blatant mess. So we will redo it. I had too much of the layout glue on here. To be honest, gluing up tapers is one of the most annoying tasks I can think of. Press it on and give it a slight twist to get it off again. You can see this slightly heavy line out here. This is where the taper in the drill chuck ends. There is about 30 millimeters of depth in the drill chuck, so we have enough clearance out the back. But you can see a very, very faint covering with blue all across the taper here. So this is really, really, really a nice fit on this drill chuck, and I won't touch it. The scaling here, it's not pretty, but we will keep it like that. I'm not going to grind it out. I'm of the opinion that instead of removing a ton of material from a good spindle to get some cosmetic marks out there, I would prefer to keep as most material for future rebuilds as possible. So we're not going to touch it again. I'm fairly happy with this. And as I said, a good inspection should be repeatable. Okay, this is about the thickness of bluing on the ID taper of the drill chuck that I'm using now. As I said, inspecting tapers, not a fan. Okay, we press it on. Now to get it off, give it a slight twist to break the taper. And as you can see, we get really a darn good result over the whole surface. It's very faint because if you put the paint on very thick, you will get an excellent print and a very good readable print. But it's meaningless because you put on 0.1 millimeter thick layer of paint. It's the same as with scraping. You want the paint to be reasonable thin. So that's what we wanted here. Looking good. I'm very pleased. While we're here, we can look at my drive system. This is just a very cheap electric screwdriver. I 3D printed this piece here out of plastic and epoxied it to the front of the cordless screwdriver. This gives me a mounting flange. 4 holes that I can put a bolt through or something like that, like here with a single M4 screw. Bolts it against my setup blocks, and these setup blocks are clamped against the sign plate. And I have a pulley on a 1/4 inch hex shaft that goes in the spindle of the thing. And I make endless O-ring belts. I just buy the O-ring cord and super glue them together end to end. Then I make a simple pulley out of Delrin or whatever I have laying around. And this goes on here like this and on here like this. A little bit of tension. You don't need a lot of tension to drive with an O-ring. Then you can just run it with power supply. It's obnoxious loud because all the straight toothed gears in here, planetary gear drive, straight toothed, and of course it's made of highest precision. One thing that I want to do to it on this plastic flanger, I want to add an aluminum spacer with a single ball bearing in it that supports the hex shaft, because right now I'm putting all this side load on it and there is just a plastic bushing in there, and that can't be good over time. I want to either to support here the spindle with a bearing or the hex shaft. I'm not 100% positive I'm going to do it, but possibly just out here on the shaft. Very high loads on it. Also the aluminum flange will have some more mounting possibilities, but this 3D printed adapter here is already a very good solid mounting surface for bolting it to things. So I wanted to talk briefly about the grinding wheels that I use on my surface grinder, and I minimized my selection. I have 5 wheel hubs for the machine currently because these are very expensive. I plan on making a set myself. These are balanceable, but with a 125mm wheel, balancing is not, well, it's good practice, but it's not strictly necessary. It's good practice to true up the wheel on its diameter and on both sides. And usually if it's not a complete crap wheel that is very inconsistent in its structure, this will be good enough with such a small wheel that you will not see any noticeable wheel hop. Still going to make a balancing arbor, and I will balance some of the wheels, those who are on balanced hubs. But something like a cutoff wheel does not need to be balanced. So what I came down to is, this is my all-purpose grinding wheel for hardened materials, hardened steels. This is a 46 grit hardness J aluminum oxide wheel. Box standard aluminum oxide, made by these people here, HB Hobby Schleifmittel GmbH here in Germany. A very inexpensive wheel. I think this is about 12 or 15 euros per wheel, and you get a lot of parts out of one wheel. So as I said, general purpose, pretty much all surface grinding I do in hardened steels, like unhardened O2, unhardened A2, hardened carbon steels, and even unhardened steels like 42 chromoly or a P20, which is 12312, which is a kind of pre-hardened tool steel. It's not really hard, it's tough, but not for hardness. Or Tulox, which comes also with a commercial heat treat. All that, this wheel. Next wheel is a little bit of a specialty. This is a Norton 3SG wheel. These are called ceramic wheel or seeded gel. These are aluminum oxide, but the aluminum oxide is modified in some way to make it more harder and more durable. This is a 60 grit wheel with a hardness J, and honestly, my grinder is too light duty to fully utilize these wheels. These wheels are for production grinding on heavy machines. They need a horsepower on the spindle to fracture the grain and expose new grains. But since they hold up so well, I find them very useful for cylindrical grinding high-speed steel with spin fixture, and for picking out corners, internal corners that don't have a grind relief, because it does hold up so well. It's a crazy expensive wheel though. One of these wheels is 55 euros and you have to buy two. These only come in packs of two. That's the reason why I have two here. But yeah, it works well. They work especially good in wear-resistant steels like D2 or high-speed steel with a high cobalt content like cobalt 5, cobalt 8 or 12. And it's 60 grit. It's a little bit finer. You don't see much difference in the surface finish between those two wheels, but this wheel, since it has a smaller grain, when you dress it, it will leave a smaller corner radius. Then, very useful, a silicon carbide wheel. Some people say you can grind carbide with a silicon carbide wheel, and yeah, you can, but you're mostly producing silicon carbide dust if you do that, because it will break down so fast. Silicon carbide as a grain has very sharp edges, is very, very brittle, and also very hard. That's the reason why it can cut carbide. But also due to the fact that it's a very hard grain and very brittle, it fractures with very sharp corners. Means this wheel will cut soft materials exceptionally well. It will cut aluminum, brass, bronze, copper. You can surface grind copper quite well with one of these if you use a grinding wax or a little bit of cutting oil. I recently used this on aluminium with cutting oil. You can still see the remains where the cutting oil washed some aluminium dust into the wheel. This is still cutting. This is not glazed up. This will still cut. Very inexpensive wheel, 12 to 15 euros. Extremely useful if you're not only doing steel. Good idea to have one around. A cutoff wheel. Since my surface grinder uses a 20mm diameter bore on the wheels, I can use angle grinder wheels. This is a 3M Cubitron 2 cutoff wheel. It's fiber reinforced, which I'm not the biggest fan for stationary use. But the Cubitron wheels, this is kind of an engineer. The regular grinding wheel is dirt glued together, and this is engineered dirt. Also glued together in a controlled way. And the Cubitron wheels really cut extremely cold. You don't put much heat into a part. They last forever and they're not super expensive. You can use them, for example, to cut off high-speed steel blanks, or if you want to make small hardened parts, you can cut parts out of a bigger chunk of hardened tool steel, or you can cut phenolic resin plate. You can cut circuit board material. You can cut some plastics cut very well with abrasive. Spring steel works very good with a cutoff wheel compared to shears. With shears, you put always a terrible amount of stress into the edge of the spring steel. This cuts relatively stress-free apart from the heat-affected zone, which with the Kubitron wheel is very minimal. And yeah, cutoff wheel, really useful. It doesn't need to be the Kubitron wheel. You can just buy a regular unreinforced cutoff wheel for a surface grinder from Norton or Turley. They work well too, but I happen to like these. And then a diamond wheel. Because, we don't only do grinding, we also do machining, and for that we have carbide tools, and sometimes we have to modify carbide tools, like necking down a shank of an end mill. And then a grinding wheel that can cut carbide properly compared to this is really a nice thing. What I like is a D126 or D125, depending where you buy it. This is the grit. It's in my opinion, a very good average diamond wheel grit that's very universal. It can do. You can remove some material with it, but it will also leave a decent enough finish. These are from a Ukrainian company. I will put the name up here on the screen. But these wheels are very, very affordable and very good quality. So that's the reason why I stick with them. Some honorable mentions: a Norton 38A 60 grit wheel, white aluminum oxide. This is your bog standard tool room grinding wheel for steel. Will cut hardened steels just fine. 60 grit. If you don't want to break down and buy a Norton 3SG wheel like these two for 120 something euros, this will do just as fine. Absolutely. 60 grit, you can pick out corners with it. It just works. These are the same wheel as this one, hardness J, 46 grit aluminum oxide, just a slightly narrow wheel. So sometimes you might have to grind a slot or something like that. Then a narrow wheel is nice because you don't have to dress down the size of your wheel that much. So these are a little bit more specialized wheels. Some of them are of my tool and cutter grinder, but they are also useful on the surface grinder. First one is a tapered cup wheel. I think this is also a Norton 38A, but 80 grit, fairly fine wheel. This is primarily used if you want to do any kind of tool grinding, or what I have used it for is to side wheel a relatively large part. A relatively tall part where I couldn't get in with a regular wheel for side wheeling. Not fun to do, but sometimes that's what you have to do. A tapered diamond wheel, D126. This is also mostly useful for tool grinding, where you need a very, very sharp edge. And also you have to be careful. The corner of a diamond wheel will break down when you use the wheel excessively on the corner. Diamond cutoff wheels. These are resin bound diamond cutoff wheels. They cut fairly nice, fairly fast. You need those to cut carbide. If you want to shorten an end mill or make specialized cutter, you need these to cut the carbide. Yeah, you can kind of score carbide with a small Dremel diamond wheel and snap it off, but usually if you do that, you create micro fractures in the carbide and hairline cracks through the entire piece of carbide, and it's a mess. Very bad results doing that. And these are also two diamond wheels, D76 and D126. This is finer, this is a little bit coarser, but the interesting thing about this one is, or both in fact, this is a full radius and this has a defined edge radius. This is a 0.5 millimeter corner radius and this is a 3 millimeter radius. What you need those for is for form grinding carbide. You can not only form this full radius, grinding a concave slot or a concave corner, but using math and figuring out your tool path, and especially if you have a DRO, you can use a formed radius wheel or a wheel like this, like you would a bullnose or a ball end mill on a CNC mill, and step off a profile and grind a profile that way. I learned this technique from Adam the machinist, and it's a very powerful technique if you want to grind carbide but don't want to pay money for a specialized form wheel and don't have a CNC grinder. So these are really specialty wheels that you don't absolutely need apart from the diamond cutoff wheels. These are super useful. I did not mention CBN wheels because I don't have a surface grinding CBN wheel. I have no experience with those. I have a CBN cup wheel for the deep bit grinder. I didn't use it very much. On a deep bit grinder, I tend to take very hard cuts, especially in high-speed steel, and this wears down the edge of the CBN wheel quite rapidly, and these are, just as the diamond wheels, very painful to dress back into shape. May be useful a regular straight cup wheel 80 grit. This is normally used on a deep bit grinder, but it can be useful on a surface grinder if you need to side wheel. Basically same, these two do basically the same, but this one with the taper has some advantages if you want to do tool grinding too. So then I had this Kuroda boring head for a very long time now. I did a video where I did a full teardown of this, and I modified it to be an ISO 30 taper to fit the new spindle of my milling machine. So I have a section of modifying a off-the-shelf ISO 30 weld-on tool holder, cut it down to fit the boring head here. I replaced the spindle of my mill from Morse taper 4 to ISO 30. I went from this Morse taper number 4 taper to a ISO 30, a number 30 taper, for various reasons. For one, these are super easy to get. These are dirt cheap, new. Everybody sells them because they're basically in every robo drill or speedio CNC mill used, and those are everywhere. You can get them used, you can get them new. This is an end mill holder, weld-on style, with a screw pushing in from the side. This is like 30 euros, and as I said, very good quality and easy to get. Morse taper 4, on the other hand, very hard to get these days because it's kind of obsolete. Morse taper 4 is used in large drill presses, lathe tailstocks, and lathe headstocks, and also it was used in manual milling machines about a lot of years ago. But these days it's quite hard to get the Morse taper 4 tooling, or any good Morse taper tooling for that matter, because there is not much need for it anymore. And when you want something more exotic than a regular collet chuck, this is a Morse taper 2 ER25. This is made by Bison in Poland. This is a very good collet chuck, but this costs about 90 euros. A ISO 30 ER25 collet is like 50 bucks. So it's cheaper, better, easier to get. Yeah, overall just the more sensible choice these days. Not saying that Morse taper is bad. Morse taper is an excellent taper, basically. It runs very true. Morse taper 4 is about the same gauge diameter here, large diameter here, as ISO 30, so the stiffness is very comparable, but the taper here in the ISO holder is very steep. That's why we call it in Germany a Steilkegel, a steep taper. And this comes out of spindle very easy. A very light tap on the drawbar is enough to have this drop out of the spindle. This needs a little bit more percussive force to come out of the spindle because the taper is very slim and it just wedges in the spindle more. So, long story short, I have my Kuroda large boring head here. Auto feed, auto facing boring head. And this is the shank I made for it. This Kuroda has the advantage of having a nice flange here where you bolt your tool shank to. And now that I changed the spindle taper of my mill, this is useless. I need this taper on here. And my idea was to take this weld-on holder, cut off all in front here, this section here, cut it off, turn this diameter here down, step it down so it fits in here, and make a flange that pulls everything together. Let me show you a sketch. Cross-section view. The yellow thing here, this is the weld-on holder. This is the original weld-on contour. The red contour is what we're going to hard turn on here. Blue is the mounting flange that pulls the weld-on shank against the boring head flange. And that's it. It's relatively easy. The only problem is these are hardened. Not much a problem. It's just you have to know that it's hardened and know how to machine it. We could either just abrasive cut off the end here, or we can hard turn the material away. I think we're going to hard turn it because why not? I think these are just case hardened, not through hardened. Nice hardened set screw. We'll take that aside. So yeah, let's take this holder and modify it. So I have the weld-on tool holder in the 6th jaw chuck, clamping on the machined outer surface here. And now I'm going to indicate the bore in. This is not strictly necessary. For a boring head, it's not crazy important that it's running true because it's a single point tool. But I still want it to be reasonably running true, just so it doesn't create any eccentric forces, which is also theoretical for a boring head because it's inherent off-center. But still, do it properly. Set true chuck, 2 micron indicator. Okay, that's already pretty close. Okay, that's pretty much 0. Now we can do our machining. I turned down the weld-on holder, the end mill holder, and now I have a 36mm register left that matches my Kuroda boring head here, just like this. And that's already pretty promising for what I want to do. Nice fit, doesn't wiggle around, good to go. So let's take this out of the spindle. So next we need to turn this OD down and also add a step on the back. I turned the ISO holder around and I clamped on the register we just turned, indicated it in true and supported it out here with live tailstock. Checked the runout in all positions, everything's well within 5 micron. And now I can turn this OD down a little bit, then also add a step on the back. I cannot turn all the way towards the chuck, otherwise I would cut into my chuck. So I'm going to stay 0.2 millimeters away, and the remaining material I can just grind away with die grinder later. This looks a little bit chaotic because we have the balancing holes, drive slot, the value chip bore, and the other drive slot in here. All that will not be seen after we add the clamping flange over it all. It will be a very clean looking modification. But right now this looks like a mess, which it is in fact. So let's check this OD. This doesn't need to be a precision diameter at all, because the flange will have an oversized bore. Okay, there we go. That's the modification to the shank done. Only thing that's left is we need to grind away this remaining material here and deburr everything. I was able to salvage this ring of the other boring head adapter that I made some time ago, and I just needed to bore it out with a step on the back side, and this goes over the ISO 30 shank here. It's captive because it's registering on this step here, and this gives me the bolt hole circle, or bolt hole pattern more, that matches the boring head. Put 6 screws in, done. That's the boring head in the spindle of the mill. As you can see, it's sticking out only 10 millimeter additional to the spindle nose. Basically, it's sticking out this length of a normal tool holder. So it doesn't get much shorter with this Kuroda boring head. It's quite a massive boring head, but if you keep the slide kind of on center and you design the boring bars in a way so you don't move the slide off center like crazy, it's very usable even at higher speeds. Currently I have it at 500 RPM. And that's spinning very nicely. At 1000 RPM is the limit for this head. You don't want to go much faster with the size of boring head, especially if you go off center. You can run this with auto facing feet. For that you engage this pin and you pull this pin out. Then you have auto facing feed, means you get extra gear reduction between this ring and this ring, which feeds the slide. As you can see, it's moving out. It's not recommended to do this by hand, of course, because safety. And then when you want to get the slide back, you re-engage this pin, disengage this one. Now you have a fast retract, basically at a normal speed. There we go, quick retract. So you don't have to spin this a million times by hand up here. Yeah, that's the Kuroda boring head adapted to ISO 30. Let's have it drop out of the spindle. I loosened the drawbar, and now I just tap the top of the drawbar with the small wrench. Doink, there it is. And here is the boring head. And the nice thing is, the ISO taper needs very little space to change tools. But hey, you don't have drive dogs in there. Yes, because ISO30, the steep taper in these machines, the steep taper without drive dogs, alone relying by friction with a threaded drawbar. Note that I said threaded drawbar. Can transfer a few kilowatts of spindle power just through the fit of the taper without needing drive dogs. If you ever ran a Deckel FP1, FP2, FP3 manual mill, it's SK40, it's a ISO 40 taper, and most tools don't use drive dogs. The collets for end mills go up to 32 millimeters, and those run without drive dogs because a drawbar with a thread pulls the taper way stronger into the spindle because people grunt down on the drawbar like crazy and they pull the taper in, and just the friction and the fit will transfer huge numbers of power. On a CNC mill, on a CNC machining center that relies on a bell-wheel washer stack to pull the taper into the spindle, that force is limited. And that's where you definitely want drive dogs, not on a manual mill with a threaded spindle. So that's my 5 cents on drive dogs. Now we have a short section about microturning. I had to make very small plungers out of stainless steel for a medical device. And that was a good opportunity to do some filming through the microscope and look at how the chip forms on the cutting edge, how the cutting oil influences the cutting effect, and just get some neat shots in general. So let's have a look. So some micromachining. The raw stock here is about 4 millimeter in diameter. This is rotor broached out of a bigger chunk of material because I couldn't get stock small enough. The tool I'm using is a brazed carbide tool with a half decent grind on it. Nothing spectacular, not even much lapped, because this is my roughing tool. I use cutting oil in this case, and you will see later why. I'm running a relatively low surface speed just because the part is very small and my lathe tops out at 2000 RPM. Here you can see why we need cutting oil. The second the cutting oil is not covering the cutting edge, the chip gets very crumbly and does not run off the tool very well. In comparison, now with cutting oil, excellent chip. At this point we're just hogging down material. We changed to a solid carbide tool that I use for finishing. But also this tool is lapped, but it also needs cutting oil in this special material. This is a heat-treated, commercial heat-treat stainless steel. It's about the toughness of 42 chromoly. Roughing out the shoulder. Well, roughing. We're taking relatively light passes here. As you can see, it's pushing out a little bit of a burr. But we will get rid of that in a second when we take our final finishing pass on the shoulder and the OD. Turning the OD, going up to the shoulder, pulling the tool back, and turning the large OD to final diameter. And suddenly the burr is gone. Changing to a 0.5 millimeter radius tool here. Touching off on the end and slowly feeding in. Once again with cutting oil until our radius is formed nicely. Cutoff tool with the leading edge of the tool ground so it's on the right side. So I can cut a shoulder on this side. Plunging in and moving sidewards, roughing out the shoulder. Taking a finishing pass. Scoring the part where I will cut it off. Cratex stick. This is a rubber bond silicon carbide abrasive. I use this for deburring and polishing before I cut it off. This just breaks all the edges very mildly, polishes all the exposed surfaces, and removes any hairline burrs. Blowing off the abrasive, adding some cutting oil, and parting it off. Sometimes parting off small diameter works without a huge nub. In this case, not so much. Huge nub left. This is, by the way, the setup I used to film through the microscope. I have the Leica MC6 microscope here and my phone. And I 3D printed this contraption. And it's just pointing the camera through the eyepiece. And when you look here at the screen of the phone, this is a pretty decent image. This is full magnification and this is lowest magnification. This is a standard €1 coin. But yeah, the zoom is pretty good here. And the image quality through the phone is also bearable. It takes something like, I think it's even 4K video, so pretty good. I can crop it to size to get it on to a normal aspect ratio. And yeah, that's the microscope stand that I built. Cheapo ring light, and that's it. Here's the clamping screw that holds it. This part here can swivel. It has 2 bell wheel washers and a nut down here to give some tension and still allow it to be adjustable to get the phone into focus, which is a fairly precise setting. It's not like you just eyeball it. You have to get it right to get a pretty decent image. Right now it's not set up properly because we have this dark haze around here. That means the phone needs to go up a little bit. Got all the parts in 3/16 stainless done. Then these will get sent out for plasma nitriding. I dragged out a very seldom used tool for me, the 6mm Lork watchmaker's lathe. Normally I don't use it much because the Emco lathe with its digital readout and the very rigid tool post and the repeatable setup tooling does all the turning, even the tiniest diameters, very well. But in this case, I need to clamp on a finished diameter with 1.6mm diameter, and I don't have a collet for the Emco with that diameter. I could either bore an emergency collet to 1.6mm or make some kind of a sleeve. But for the Lork, I have the collets in a 0.2mm increment. Means I have a 1.6mm collet, and I can easily hold the part in here to face the back with this tiny high-speed steel turning tool. The way I'm running the watchmaker's lathe is probably a disgrace to every watchmaker out there. But yeah, I don't care. Okay, faced off the end of the part. Now we take our tweezers and get the part out of here and drop it in the finished part test tube. And here's the next one. Grab it on the small diameter, insert it in a collet, kind of place it in the right spot, tighten the collet. It has this super cute little draw tube with a Bakelite handle on here on the back to tighten the collet. And that's enough to tighten these tiny 6mm draw style collets. By the way, this headstock of this watchmaker lathe is running in plain hardened steel bearings, and the shaft itself is also hardened, so it's running hard on hard. And you just add a tiny amount of super thin oil, spindle oil, to them, and they will probably last forever. So in the final section, I wanted to talk about some missing tools that I forgot in the last video, where I talked about the drilling with the carriage on the lathe, and I had some questions, and I have some things to add on to that. So let's have a look. In the last video where I talked about drilling with the carriage, which was a very controversial topic, one person even said they would fire me if I did that in their shop. So that's a very radical opinion, I think. When I did that video, I forgot to mention some things. First of all, I want to show the heavy-duty CNC mimetic drill chuck in use. It's here in the boring bar holder. The VDI interface fits into a regular round boring bar holder. And as I said, these are worm drive. When you spin, you go in here with an hex and you spin it, you will extremely slowly close the jaws and exceed a ton of holding force on the tool you're holding. These are especially nice if you want to hold a tap, because these will under no circumstances loosen when you run the lathe in reverse. Never. It's a good idea to use a torque wrench on these, because if you over tighten them, you will strip the worm in here or the worm drive. They have somewhere on here, there is a torque value that you should tighten them to. And then a inexpensive torque wrench like these, which are used for insert tooling. These are single torque, fixed setting, and you just put in the fitting key and you tighten your chuck with this. So I use this for large taps like M10, M12, or large pipe thread taps. Won't let loose on a drill. So that's one thing. I was asked if I use the setup for reaming too, and yes, I do it. Either by just holding the reamer in a drill chuck, or if I have to do a lot of parts, I will set up a floating reamer holder. This one is made by Regofix, a Swiss company, probably known for making collets and collet holders. Its number is 820005. It has an ER20 collet seat in here for regular collet, and this flush mount nut. So this is basically an ER collet chuck with an integrated floating tap holder. Means this has about 1 millimeter to each side of give, so the reamer can self-align in the pre-drilled and pre-bored hole. Very useful also for tapping, especially when you tap in plastic and your tab is not 100% on center with the pre-drilled hole, if you hold the tab rigidly in a drill chuck or a collet, you will bore out the thread with the tab and make an oversized hole. With the floating reamer holder or floating tab holder, that will not happen. So that's the benefit of this. Don't use it a ton, but when I do, it's nice to have. Relatively slow to set up due to the collets. Then something I made for myself. This is just a sleeve. I think this is turned from 42 chromoly with regular commercial heat treatment. Then I had a plasma nitride, so it has about a 0.7 millimeter thick hard layer. The plasma nitriding doesn't change any dimensions, it just makes it very tough and hard, and also a little bit of corrosion resistant. And this is so I can use the Deckel S20x2 style 355E collets that I have, for example, for the tool and cutter grinder. I can use these collets in the same boring bar holder. I can do this either, for example, if I want to hold a small tool or a small drill with good run out and very little overhang. For example, when I change tools a lot, I don't want to move the carriage a lot because the drill chuck is reasonably long, and change to a very short tool, and this just gives a little bit more options. Another option, of course, is a straight shanked ER collet. I use this with a reduction bushing, also in the boring bar holder. This uses ER20 collets, just as the Rigofix floating reamer holder here. Also, this is nice for holding. And lastly, what I absolutely forgot to show is my OD threading setup if I'm not single point threading. These days, most threads I single point, but for low quality threads, I just use a die. And this is a floating die holder. It's just a sleeve of a pin and internal bushing, and can exchange the die holder in there. And I have a full set of die holders. I made some of them myself, and some came with it. This is usually the accessory for a very cheap import revolver head, quick change head for a tailstock. But this fits also in the boring bar holder. I hard turned the OD down so it fits. And yeah, you can go M3. Just tighten those two screws, and you're ready to tap or thread. M3, M4, M5, 6. This is 8 and M10. And this works reasonably well. In hindsight, I would not need the sliding motion here, because the carriage moves so freely. It would just pull the carriage along, even with an M3 thread. So that's my OD threading setup with the carriage. I think that's all of the tooling I use for now. Hey, you're still here. That's great. Thank you all for watching. I hope you enjoyed this mishmash of content. Thanks for the ongoing support. Thanks for commenting. Thanks for engaging. Just thank you. I'll be back.